James Webb looked at the early universe and found something it cannot explain. In nearly every image of the universe's first billion years, the same object. Little red dots, impossibly small, impossibly bright. And they don't match anything we've ever seen. Not a galaxy, not a black hole, not a star. Something else entirely. And here's the part that should terrify you. 600 million years after the Big Bang, the universe was filled with them. Then, 1.5 billion years later, they vanished. Completely. Gone. Whatever these things are, they existed for a specific window of time, served some unknown purpose, and then disappeared like they were never there. Physics does not have an answer for this, but one man predicted it 16 years ago. Let's start with what we know. These little red dots are tiny, no more than 500 light years across. That's 200 times smaller than our own galaxy. But they burn with the brightness of something 1,000 times that size. And they are red. Not just from distance, from something deeper, something in the light itself. So scientists did what scientists do. They built a theory. Theory number 1, starburst galaxies. The logic was clean. Hot young stars produce exactly the kind of hydrogen signature these dots were showing. A spectral fingerprint called a Balmer break. Dense stars explain the brightness. Dust from those stars explains the red color. It almost worked, except the math destroyed it. Researchers at the University of Texas ran the numbers and found these objects only had 1% of the dust needed to explain their redness. 1%. And to be that bright using only stars, the stars would have to be so close together they'd be constantly colliding. The gravitational chaos alone would tear the whole thing apart. So they moved to theory number 2, active black holes. Black holes made sense. They explain the brightness. They explain the single point of light with no visible structure. And the broad emission lines, gas spinning at thousands of kilometers per second. That's exactly what you'd expect around a feeding black hole. But then someone asked one question. Where are the X-rays? Active black holes always emit X-rays. Always. James Webb found 0. And it got worse. These black holes appeared to be 10% of their galaxy's total mass. In our universe, that number is 0.1%. 100 times too big. Impossibly oversized for the galaxies they were supposedly living in. Both theories, dead. And then a single object changed everything. In July 2024, astronomers found one little red dot with a spectrum so extreme, they called it the cliff. And what was hiding inside it rewrote everything. Astrophysicist Anna DeGraff at Harvard-Smithsonian wasn't looking for theories. She was looking for the rarest, most extreme objects in the sky, the things that sat furthest outside every expected distribution. So she built the RUBIES survey, Red Unknowns, Bright Infrared Extragalactic. Nearly 60 hours of Webb time, 300 red sources. The largest spectroscopic sample of little red dots ever assembled. What she expected? Clarity. What she got? Something far stranger. Most of the objects turned out to be dusty galaxies, or galaxies that had already stopped forming stars. Black holes powering galactic cores. The usual suspects, divided between the two failed theories, both partially right. But then there was a subset. Objects with the V-shaped spectra, the broad emission lines, the point source light. All the signatures that had resisted every explanation. And they didn't fit anywhere. And then, 11.9 billion light years away, DeGraff's team found it. A little red dot with a Balmer break so steep, so vertical, so extreme, twice as strong as anything ever seen in the ancient universe. They named it the cliff. a near-vertical spectral wall. Not a gradual slope like a messy galaxy with layers of different stars and gases. A cliff, which means one thing: a massive, almost perfectly pure envelope of hydrogen gas, surrounding something we couldn't quite identify. On one side of the data, a supermassive black hole signature. On the other, the dense hydrogen atmosphere of a star. The extreme properties of the cliff forced us to go back to the drawing board, DeGraff said, and come up with entirely new models. She had found something that was, impossibly, both. In 2008, theoretical astrophysicist Mitchell Begelman at the University of Colorado published a paper. He described an object he called a quasi-star, a black hole forming inside a dense cloud of pristine hydrogen gas. Rather than the gas dispersing, it stays bound. The black hole sits at the core, feeding. The outer envelope glows, not from nuclear fusion, but from the sheer energy of the black hole consuming matter at its center. From the outside, it looks like a single, enormous star. But inside, it's a supermassive black hole. No one paid much attention in 2008. There was no telescope that could ever see something like this. Then James Webb launched. Here's how the quasi-star, the black hole star, solves every mystery at once. The missing X-rays? Not missing. Trapped. The hydrogen envelope is so thick, so dense, X-rays can't punch through. They get absorbed and re-emitted as the red optical light we actually see. The missing dust? There is no dust. The redness comes entirely from the opacity of the gas. No dust needed. No shortfall to explain. The overmassive black holes? An illusion. In a black hole star, photons don't travel cleanly outward. They bounce through the thick envelope. Every collision shifts their wavelength slightly. The cumulative effect makes the emission lines appear broader than they are, causing scientists to overestimate the black hole mass by 100 to 300 times. Correct for that, and the mass drops back to exactly what we'd expect. 3 unsolved mysteries. 1 object. Predicted 16 years before we could see it. But this isn't just about a strange object in the early universe. This is about how every supermassive black hole in existence, including the one at the center of our galaxy, actually got there. Here's the real crisis. Supermassive black holes should not exist this early. We know they were already billions of solar masses, just a few 100 million years after the Big Bang. The conventional model says black holes should be 10 to 100 solar masses by that point in time. Not billions. The math doesn't work. And nobody could explain how they got so big so fast. Until now. Black holes have a speed limit on how fast they can feed, called the Eddington limit. It's set by their own radiation pushing back against infalling gas. But a black hole star bypasses this entirely, because the limit is no longer calculated on the black hole's mass alone. It's calculated on the entire gas envelope, which is vastly larger. The black hole gorges, growing thousands of solar masses in just a few million years. The envelope slowly cools. It hits a temperature floor, around 4,000 Kelvin, and radiation pressure wins. The envelope blows away. The quasi-star phase ends. What remains is a naked, supermassive black hole, ready to anchor a galaxy, ready to pull in billions of stars, ready to become the monster at the center of everything. And 1.5 billion years after the Big Bang, when the conditions for this process no longer existed, the little red dots vanished, because their job was already done. If you want to understand what happens when a supermassive black hole stops feeding and starts trapping everything, including light, that video is on screen right now. Watch it.